Good morning. This is chapter 4, Work and Energy. Now, before we dive into this chapter, I do want to encourage you to understand how each question is worked out. I am sure you know that memorizing stuff will not help. You have to really know. And to know, you have to take time. You can't be like, okay, let me finish this as quickly as possible. That's going to be a waste of time. So please look at each question carefully and understand how it's been worked out. And then things will begin to become easier. So let's go to the first one. David pulls his younger brother in a sled on an icy surface. Assume no friction with a force of 75 Newton. So David is pulling his younger brother in a sled with a force of 75 Newton at an angle of 30 degrees above the horizontal. He pulls the sled a distance of 15.0 meter. What is the work done by David's pull? How much of that work goes into increasing the sled's kinetic energy? Now, I'm going to draw a diagram right here, a simple diagram to understand what's going on. So let's say that's the sled, and the force is being applied that way, and it's making an angle of 30 degrees above the horizontal. So the force itself is 75 Newton. That's the force at an angle. But the sled is moving this way, right? So we can see there is an angle between D, which is the distance moved, and the force. That angle is 30 degrees. So I could have drawn the force here. It doesn't make any difference. Okay, I can do that. Draw the force here. The angle is 30. So it doesn't matter where you show the force. The angle between the force and the distance is 30 degrees. The formula for work is FD cosine theta. F is the force, D is the distance, and then you have a little trig here, cosine of the angle. On your calculator, please make sure that it is set up in the degree mode. So you have two modes. You should know how to go and change it. It could either be in degrees, which is correct, which is what we want, and the second mode is radians. We do not want it to be in radians. Actually, there is a third mode called gradient. So please make sure that your calculator is in the degree mode, okay? And if it is in the degree mode, then you will see that when you enter cosine and hit 30 degrees, you should see this number pop up, 0.8660. That is the value for cosine 30 degrees. So now that we have the force, the distance, and the cosine of the angle, multiply them, and you get 974.3 joules. Joule is the unit of work. It's also the unit of energy because work and energy are related. Why are they related? Energy is the ability to do work. So if you have 10 joules of energy, you can do 10 joules of work. So considering significant figures, the work is 9.74 times 10 to the power 2 joules. Okay? Because you always go with the smaller number of sig figures, which is like 3 here, 3 here. There's 4 here, but you go with the smaller number. So the answer should have the smaller number, which is 3. That is the first one. It's also asking how much of that work goes in increasing sled's kinetic energy. Now, you don't have to work out anything because there's no friction. All of the work done becomes the kinetic energy. So the answer to part B is exactly the same as the answer to part A. Okay. You don't have to work it out. And that's only because there is no friction. If there were friction, then a part of the energy would be lost in overcoming friction. All right. So let's go to the second one. Where's the second question? This question says, how much energy or work, you see that right there, work and energy are interchangeably used. How much work or how much energy is required to increase the speed of a 1200 kilogram car from 10.0 meter per second to 30.0 meter per second. So when you step on the gas in your car, it speeds up and the engine has to do extra work. So in this case, you're asked to find the extra work required to make the car go from 10.0 to 30.0 meter per second. So the idea here is that the kinetic energy of the car increases. And the formula for kinetic energy is 1/2 mass times velocity square. So if you find the initial kinetic energy, the final kinetic energy, take the difference between them, you will get the work done. That's what we're going to do. So the mass is given, the initial velocity, and the final velocity. So first, let's find out the initial kinetic energy, which is what is done here. 1/2 times mass times the square of the initial velocity, as you can see. Now 1/2 times 1200 is 600, and then 10.0 square is 100. That gives you 60,000 joules. Now do the same for the final kinetic energy. You get 1/2 times 1200 times 30.0 square, which comes out to be 540,000 joules. You see that this is much bigger than this. So the work is simply the difference. Work is the final kinetic energy minus the initial kinetic energy, which gives you 480,000 joules. And in the scientific notation, it's written as 4.80 times 10 to the 5 joules. So that is the answer for number 2. All right, let's move on to number 3. This question is about lifting an object vertically. When you lift an object vertically, what happens is its potential energy increases. So this problem is to do with change in potential energy. The formula for potential energy is mgh, where m is the mass, g is, the acceleration due to gravity, and h is the height from the ground. So let's read the question. A lab technician lifts a piece of equipment weighing 150 newtons. All right, note something. What's given is the weight, it's not the mass. So what is given is actually mg. See, m into g. And it's lifted straight up by 3.0 meter and holds it there. How much work does she do in lifting it? So to calculate the work, all we need to do is MGH. MG is 150 and H is 3.0. Just multiply them and you get the answer. Now here, what's written here is the weight right here, which is again, which is mg. Hope that makes sense. So all we're doing is mg times h. So another way this question could have been asked is, what is the increase in potential energy of the equipment? I hope you know the answer. Whatever is the work is the same as the increase in potential energy. Okay? So keep that in mind. That's number two. Number three. Oh, we moved to number four. So I think I missed number two. Oh no, 2, 3, 4. I was right. Accelerating a cart on a level surface. We did something similar to this, but there's a slight change. A constant force of 250 Newton is applied to a 70-kilogram cart. The force is given, the mass of the cart is given, it's initially at rest on a level frictionless surface for 12 meters. So there is no friction and the cart is moved 12 meters. What is the final speed of the cart? So what's given is the force, the mass, the distance moved, and the initial velocity. The idea here is the same as in problem number 2. Work done is the change in kinetic energy. See that? And how do you find the work? Force times distance. Now, some of you may be thinking, why don't we use cosine of the angle? Because the angle in this case is 0. It's the force is that way, the movement is also that way. So the angle is 0 degrees. If you take cosine of 0 degrees, you're going to get 1. So if you wanted to use that formula, there's no mistake there, no problem. Only thing is, it will not change the answer. So you would get 250 times 12 times 1, which is 3,000 joules. Okay, going back to the question. So we now got the work done, but we know that the work done is also change in kinetic energy. Now, the initial velocity is 0. So look at that, work is change in kinetic energy. This triangle shows change. Whenever you see that triangle, it stands for change. So change in kinetic energy. That is 1/2 mass times the final velocity square minus, actually it should be 1/2 mass times initial velocity square. But the reason why it's not written is because the initial velocity being 0, this whole quantity becomes 0, right? This whole quantity, that's why. And so now we know work is 3,000. See that? 3,000. So 3,000 is equal to 1/2 times mass times square of the final velocity. 70 divided by 2 is 35. So now we have 3,000 is 35 times square of the final. We got to divide both sides by 35. That's what is done. Divide both sides by 35. 35 cancels out here, and you get 3,000 by 35, which is this number. And because it's a square, you have to take the square root on both sides. When you do that, you're going to get square root of this number, which is 9.26 meter per second, which is the final speed of the cart. There you go. I hope that makes sense. Let's move to number five. All right, what do we have here? A spring-driven pellet launcher fires a 15-gram pellet. Oh, so now we have a compressed spring and then let go, it fires a pellet, just like a toy gun. To cock the launcher, a person pulls back the spring with a constant force of 30 Newton. So you had a 15-gram pellet, you have a force of 30 Newton over a distance of 4.0 centimeter. See, there's a danger there. Centimeter is never used. We got to change it into meter. Anyways, you apply this force and cock it through that distance in meters. You're doing work, are you not? First, we have to find that work. And then from question number three, we know that the work done is potential energy, but this time we have a different type of potential energy. It's called elastic potential energy. Whenever you compress a spring or stretch a spring or pull a rubber band, it's the energy is being stored as elastic potential energy. Okay, so therefore, to find the work, all you got to do is multiply the force with the distance in meters. See, centimeters changed into meter here. How? Dividing by 100, because 100 centimeters is 1 meter. That's why you go from this number to this. And then work is 1.20 joules. And this becomes the kinetic energy of the pellet. Okay, so the elastic potential energy becomes the kinetic energy. Let me make that clear. Three things now. The work done becomes the elastic potential energy, and when it's released, all of the elastic potential energy becomes kinetic energy. I hope that's not too much. We know the formula for kinetic energy is 1/2 times mass times velocity squared. So we'll set that equal to this number and solve for the velocity. Got to be careful there, because to solve for that velocity, you got to multiply both sides with 2, right? Then divide both sides with the mass. Why did we have to do that? So that the mass gets canceled here and the 2 gets canceled. That's why you have this quantity there. Look at that, 2 times 1.2. Oh, by the way, the 15-gram had to be changed into kilogram, and that's done by dividing it by 1,000, because 1,000 grams is 1 kilogram. So that's how we get that. And then that comes out to be 160. But remember that it's the square of the velocity. So take square root on both sides. And they'll give you 12.65 meter per second. And since there are only 3 thick figures here, you have to round it up to 12.7. So it only has 3 thick figures instead of 4. Let's go to the next. Running up a hospital staircase. Don't do that, but somebody's doing it. And that somebody is a patient. A 75.0 kilogram patient ascends a flight of hospital stairs that lifts him up vertically by 8.0 meter. So he's going up. Whenever an object goes up, it gains potential energy. Remember? So the mass is given, the height is given, and he does this in 10.0 seconds. Time is given. Why? Because you're asked to find power. Power is work over time. So in this case, you got to find the work and then divide it by the time. Remember that the work is the change in potential energy, which is what? MGH. So that's why work is calculated here as MGH as times G times H, all in proper units. That gives us 5,880 joules. And then once you get the work divided by the time in seconds, so you get this. So remember that work is in joules, time is in seconds. Joule per second is called watt, which is the unit of power. Okay? And that's written in the scientific notation this way. So quite simple. Just you got to know what kind of work is being done. Here it's potential energy, so MGH. Okay? Let's move on to number 7. Constant velocity motion against a resistive force. All right, let's see what you got here. An engineer pushes a medical cart so that it moves at a constant velocity of 2.0 meter per second. So we have the velocity while overcoming a resistive force of 15 Newton. So the force is given and the velocity is given. You're asked to find the power. Let me show you something. It's going to be a new formula, but I want to bring it out. So power is actually work over time. But remember that work is force times distance. So now we got that over time. And if you take distance over time, then what do you get? You get velocity. So we have a new formula now. Power is force multiplied by velocity. Isn't that simple? Okay, so you're given the force, you're given the velocity. All you got to do is multiply them to get the power. Now, this question is important because we're dealing with a new formula, which comes from putting those two ideas together. Okay, so that's number 7. All right, do we have any more? Oh, we only had 7 questions. And I think these 7 questions are enough, more than enough, for you to complete the homework with a good understanding of what you're doing. Now, I started this recording telling you the importance of understanding stuff for which you need to take the time and effort. The good news is that once you understand it, you will not have to memorize it several times. But unfortunately, most of the time, I have to say this, students try to do it quickly, and that process is called memorizing stuff. And yes, although it's going to be quick, you're going to end up being confused because you really did not take the time to understand what's going on. So I'm being very honest and I'm trying to help you when I say that the first time when you watch this video, you should make an effort to understand what is going on. If you do that, you will not regret. After having understood this, if you do the homework without sneaking a look at this, like go back and forth and see what I did and just replicate the motion, that's not going to be very useful. I know you may have to take a look once in a while, that's fine. But if you're simply opening it side by side and copying the motions, then you are putting yourself in trouble. So really understand it, understand what's going on, you'll be good. All right, wish you all the best. See you on the next one. Thank you.